We have for you today a special present. Your assignment is tomorrow, after you finish acing exam 1. You get a half hour for beer and pizza, and you can start on this. The due date is on there. If it becomes necessary, I'll extend the due date. I won't shrink it, probably won't extend it. But if the due date changes, it will be changed by extending rather than shrinking. It'll depend where we are on material content the time we get to the due date. A couple of announcements. I discovered a blunder to one of the questions on exam 1 from fall 13. Since that's the most recent exam 1, you are likely looking at it or have looked at it in prep for tomorrow's exam 1. I made a correction. The question which I corrected had to do with writing a complete system inventory for solute-derived species. I think it was ammonium hydrogen carbonate solution. Of all things, I left out hydroxide ion and hydronium, which of course are also provided to that system by solute species. So, I flunked that question. But for your benefit, I fixed it and reposted it. Olivia Rissett has decided to extend office hours today for the benefit of you who wish to see her on an out-of-class basis. The information is there. And I'm happy to say that when I visited the surgeon yesterday, he took one look at me and he says, "We have to fix that." I said, "You're damn right." February 27th. Surgery's booked for about noon. I should return home about 4 o'clock that afternoon. And if things go according to my plan, I'll be here the Friday immediately after. To me, missing class is more painful than anything else. I like being here. But if I'm still physically incapable, Mr. Mosid will fill in for me that day. He may fill in for me some days before then, because on occasion, this thing is pretty damn grievous in the morning. But so far, I'm managing to fight through it. Now then, Friday, the 28th of February, you probably know is the day right before spring break. I purposely selected a slot for surgery so that if I need a couple of days to recuperate, I will have such available during the spring break week. But my plan is, just like I did the last time I had a hernia repair, which was here 5 years ago. Same surgical group. When I left the hospital in the early afternoon, because that one was fixed in early morning, they said, "Go home." And I did. I got in my car, I drove here, and I went to work in my office. That was not part of their plan, but I don't give a damn was part of my plan. Now, I'm not saying everybody should operate the way I operate. I just operate in a fashion which does the best to keep me happy. And laying at home in bed does not keep me happy. I want to be here thinking about chemistry. Now then, let's wrap up the material for which you are responsible on tomorrow's exam 1. Many of you have already been through this. But from the information I received, all the discussion classes didn't quite get through this stuff on hydronium ion concentration for water solutions of polyprotic Bronsted-Lowry acids. First category. 3 categories of Bronsted-Lowry polyprotic acids, N bases. Based on acids, the parent acid is strong and molecular. The only common example of such is sulfuric acid, which you know about. If for no other reason, it's in our acid-base table. Category number 2, the parent acid is weak and molecular, as we shall see, but this is not part of exam 1, because I didn't know if we'd be able to get through it. I don't like to rush through this stuff. This is the easiest calculation. Nothing to it. Because you'll see when we talk about this, even though there are 2, perhaps 3 ionization constants for the acid, Ka1, Ka2, perhaps Ka3, as for phosphoric acid, you only have to consider Ka1 to correctly calculate hydronium ion molarity for the system. Well, that's easy. And then comes the fun one, where the parent acid is a hydrated metal ion. Because as we shall see, with this kind of a solution, you will almost always have to consider Ka1 as well as Ka2. The upshot of which is with 2 equilibrium equations written, you will have 4 unknowns and only 2 equations. Can you solve for 4 unknowns with 2 equations? No. You got to have at least 2 more simultaneous independent equations involving the same set of unknowns. Which means we got to be able to write at least 2 other equations. We've already learned how to write 1 additional equation. It's called material balance. Remember that? Well, when we get to that, we'll start putting material balance to far greater use than we so far have. Do you remember what the 4th equation will be based on? Charge balance, you betcha. Which is also, really, a simple consideration to apply. But because of the 4 unknowns and having to deal with 4 equations, this is by far the most challenging of these issues. This will, of course, come after this, and neither of these topics are part of tomorrow's exam 1. So on we go with the last consideration, which in fact is part of tomorrow's exam 1, which is the case where the parent acid, polyprotic, is strong but molecular. Common example, sulfuric acid in our acid-base table, so we'll consider sulfuric acid solution, water solutions thereof. First, the directive, if you will, on page 1841, I mistyped the formula for the sulfuric acid molecule. Fix it so as to not be confused. And you know why I write the formula for the sulfuric acid molecule like this rather than H2SO4. Because if I give you this H2SO4 formula, a somewhat more condensed formula than that, and I ask you to get at the most important property of that molecule as it is for any molecule, its structure. Likely you'll write a Lewis picture where the hydrogen atoms are covalently bonded to sulfur, and you'll be wrong. That's why I don't like that formula. Because if I give you this formula, you'll never bond the hydrogen atoms to sulfur. You'll bond them to oxygen, which is correct, as this formula tells you. This is generally speaking a tetrahedral molecule. Sulfur central atom, oxygen, oxygen, OH, HO as the peripheral groups. More on that later. Now, back to the pH consideration. As we noted last time, the chemistry that occurs when sulfuric acid solute is dissolved in water is this reaction, which goes to an extent of 100%. That guarantees that the hydronium ion molarity is at least M sub I, the label on the bottle. And reaction number 2, the ionization of hydrogen sulfate ion, which is the conjugate base of this molecule, but hydrogen sulfate ion does not behave as a base in water solution because it's a good deal weaker base than water. But it does behave as an acid in water solution You find it in the acid column. You find it with a Ka value of 1.2 times 10 to the minus 2. So it's a weak acid of appreciable strength. Which means if 2 goes to any extent greater than 0%, which is almost always the case, the hydronium ion molarity for a sulfuric acid solution is bigger than m sub I. So for this solution, the true hydronium ion molarity is bigger than 0.0010. Now, for reasons I have not yet recognized, some students have difficulty realizing that when you look carefully at 1 and 2, you recognize that the hydronium ion molarity is in fact m sub I plus the sulfate ion molarity for each and every sulfuric acid solution, so long as the first reaction goes 100%, which it will unless you're dealing with 12 molar sulfuric acid solution or some very unusually high concentration sulfuric acid solution where you just don't have enough water in the pot to ionize all the sulfuric acid molecules. So, to try to make sure you see this, as well as this, that m sub I is equal to the sum of these two terms, which means the hydronium ion molarity is m sub I plus this, and if m sub I is this plus this, then the hydronium ion molarity is also hydrogen sulfate ion molarity plus twice the sulfate ion molarity. So we're going to play a game. I'll write 100 over sulfuric acid. Imagine then we made a solution by dissolving 100 sulfuric acid molecules. After dissolving the 100 sulfuric acid molecules, following the first reaction, what's the number I write over this? What's the number I write over this? Bingo. Stoichiometry tells me that. And I go back to the 100 over sulfuric acid and line it out because it's all gone. That's done. Which tells you, any textbook which writes H2SO4AQ on their pages has charged you a lot of money for garbage. Garbage! Because H2SO4AQ, unless the solution is extremely concentrated, is a myth. There are no such molecules in the pot. Now then, when reaction number 2 starts, but has not yet proceeded, how many of these do I have? 100. All right? Now, since the second reaction is governed by equilibrium control, it will go to an extent which is between 0 and 100%. Nothing fancy about that. Pick me a percent to which you wish to decide reaction number 2 proceeds. How many vote for 40? How many vote for 50? How many vote for 60? Looks like most people want 50. Who cares? Doesn't matter. All right, we'll take 50. That means, how many of these 100 ions go away? 50 of them. That means I make how many of these? That means by this reaction I make how many of these? 50. So how many of these total will I have? 150. Bingo. The first reaction plus the second reaction. And how many of these will remain? 50. So I'll line this out and write 50. Now do you see this plus this? 50 plus 50 is m sub I? Because there's m sub I. Right? That's the label on the bottle. That's all there is to it. If you decided, as some of you wished, that this reaction went 40%, well then this would be 40, this would be 140, and this would be what? 60. Well, nothing fancy about this. I hope that shows you immediately why this relationship, or where this relationship comes from, and that it holds, and how this relationship holds. Okay? That's all you need to know. if you know these relationships for sulfuric acid solution, you can solve quick and fast for the hydronium ion molarity for any sulfuric acid solution. That's what you need to know. And those reactions, I mean, these equations come from the two pieces of chemistry, the two reactions, which we must consider for sulfuric acid solution, because they're the two reactions which happen when you make sulfuric acid solution. Question. If the sulfuric acid solution is dilute, that means the numerical value for m sub I is a small number. Can I expect 2 to go to a large extent? Yes, emphatically. You tell me why. If sulfuric acid solution is quite dilute, or doesn't even have to be quite dilute.
Because there's more water for it to react with.
Well, I don't want to hear it. Don't ever say it.
There's more water for the sulfuric acid to react with.
Sulfuric acid. There's no sulfuric acid left when we get to step 2.
As you increase the amount of solvent, you increase the percentage of ionization. Because of the Chalet's principle, you have more of the reactants to go produce more product to be equilibrium.
This is true, but that's only part of the puzzle. Whenever we dilute, a weak acid or weak base will react with water to a larger extent. But what does percent ionization depend on? Does it depend only on dilution factor? What else does it depend on? Ka. And we talked last time to realize that if a weak acid had the Ka value of 1 times 10 to the minus 7, by dilution, you can get it to go to an extent of 50%. That means if Ka is bigger than 10 to the minus 7, by dilution you get it to go past 50%. And if Ka is smaller than 10 to the minus 7, you can't get it to go 50%. I don't give a damn how dilute the system is. Explanation of this is in the notes. I hope you read it. What is Ka for this HOSO3 minus? It's 1.2 times 10 to the minus 2. How does that compare to 1 times 10 to the minus 7? It's enormously larger. By what factor? Is 1.2 times 10 to the minus 2 bigger than 1 times 10 to the minus 7? I'm listening.
1.2 times 10 to the 5th.
1.2 times 10 to the 5th. That's only 120,000. So guess what? If you've got fairly dilute sulfuric acid solution, that second ionization reaction is also going 100%. Now what is the minimum m sub I value for which it will be 100%? And any smaller m sub I value will of course be 100%. You can calculate that. I've often asked that question on exams. In the summer, when you take real exams. But we'll talk a little bit more about that later. Let's do first some simple analyses of sulfuric acid solutions, and then you should get the idea of how to deal with the question I just posed. All right, we talked about this. Now then, is this sulfuric acid solution fairly dilute? Yes. Well, 1,000 molar, that's fairly dilute. Okay. Gee whiz, because you probably say, what the hell does he mean when he says dilute or concentrated? And that's a perfectly legitimate question. Something you should ask. So I will say that gee whiz, 10th molar or higher molarity is fairly concentrated, and less than 10th molar dilute, less than 100th molar, 1000th molar, pretty dilute, fairly dilute, significantly dilute. Now then, since the original question was, let's get the hydronium ion molarity for 1000th molar sulfuric acid solution to 2 sig figs. Let's go back to that solution. Here's Ka, chemical version for hydrogen sulfate ion. And here's what we have. Following from these relationships which we have just derived. For this solution, the hydronium ion molarity is m sub I plus sulfate ion. Sulfate ion molarity is sulfate ion molarity. And hydrogen sulfate ion molarity is m sub I less sulfate. There it is. So, you got 1.2 times 10 to the minus 2 equals this. How many unknowns you got? 1. You can solve it. Now, students often take this, and instead of writing sulfate ion, they'll write X. Now, that's not evil. But if you lose sight of what X is, because in this system, what can X be? X can be M sub I. X can be the sulfate ion molarity. X can be the hydronium ion molarity. X can be the hydrogen sulfate ion molarity. So I urge you to stick with this, because that tells you what the heck you're looking for. I mean, if you're so concerned about saving a little bit of graphite or ink that you want to write X instead of sulfate ion molarity, be my guest. But be careful. Because if you lose sight of what X is, you're going to get the problem fouled up. I don't want that. And I know you don't want that. Now, how do we solve? Ha ha! This is a quadratic if you expand it. I'm not going to subject this to that relationship, which is very important in algebra class, but in chemistry class it has you lose sight of chemistry. I'm not going to do that. I'm going to take advantage of what we were just talking about. That percent ionization depends on dilution factor and Ka. This is a fairly dilute solution, and Ka for hydrogen sulfate ion is 1.2 times 10 to the minus 2, which is a hell of a lot bigger, 1.2 times 10 to the fifth bigger than 1 times 10 to the minus 7, which means percent or extent of ionization is appreciable, to say the least, for hydrogen sulfate ion in this solution. But from a numerical simplification standpoint, when you start speculating on percent ionization to solve a relationship like this, what percent ionization should you start with first always? 50%. Because if you start with 50%, this term will always have what value? What is always the value for this term if you start with 50% ionization extent? I want the answer that's always correct. What is it? 50% of M sub I. What's 50% of M sub I? Half of M sub I. That's it. Right? Notice that. Half of M sub I. Here's M sub I. That makes this 0.00050 and this 0.0050. So there's what we get for the hydronium ion molarity. Now then, if I take 0.0050 and add it to this, I get this. How does that compare to this? Smaller than this. Well, if it's smaller than this, what's the true percent ionization compared to 50%? Greater than 50%. Okay? So we tried half of M sub I, corresponding to 50% ionization extent. Maybe what I said a moment ago didn't quite come out quite clearly. Point is, when you try 50% ionization, you're looking at half of M sub I as your value for X, or your ionization extent. Okay? Let's say it that way, because I know that way is correct. So we tried that on for size. 50% ionization, that gives us this. And that's a lot smaller than this. So I know that the true ionization extent is bigger than 50%. Well, what do you want to try next? Let's try %. All right? Now here comes the hard part. 80% of this number. Now, I've seen students in my office many times. If I ask them to give me 80% of 100, They'll say 80, no problem. But if I ask them to give me 80% of that number, they have a fit, because that number is a number smaller than 1. Because you people, if you do this, have made a habit of taking decimal fractions, and gentlemen, to your damn calculator. Don't do that. Here's the calculator you want to use. Do I sound emphatic about this? This is the calculator you got that's great, grand, and the one you got forever. Use it. Don't let it sit around collecting cobwebs. See this? You come into my office, I give you 80% of that, you use this, I'm going to smash this. Then you have to use this. Ha ha ha. So I'll force you to do it the right way. It ain't my way, it's the right way. Tell me, if I try 80%, let's write it over here. What do I get for the fraction? What will be the sulfate ion molarity? That it? What do I got for the hydronium ion molarity? What have I got for the hydrogen sulfate ion molarity? 0.0. You telling me this is hard? You want to make it hard? Use that damn push button thing. Then you'll make it hard. Now watch out, because this is really tough. This number divided by this number. How about that? It's not hard. But you want to make it hard, use that damn push button thing. Because when you do, what you're doing when you use that push button thing is you're turning off this computer. And that makes everything hard. Because you are no longer thinking. You ever see the movie The Paper Chase? Too bad. If you get a chance to see it, see it. Wonderful movie. John Houseman plays a law professor, I believe at Harvard, wherever, one of the big-time Ivy League schools. Students come into his lecture class first day, and he looks at them, and he says, "You all come in here with a skull full of mush, but when you leave, after I finish with you, you'll be thinking like a lawyer." Well, I like to say, you come in here with a skull full of mush, and when you leave, you'll be stinking like a chemist. Stinking wonderfully. How about that? Tell me, is the result of this arithmetic bigger or smaller than Ka? Smaller. So now I know the ionization extends bigger than 80%. Well, I got this ionization extend in a pretty small box, right? It's 81%, 82%, 3%, 4%, 5%, 6%, 7%, 8%, up to 100%. And you can see at a glance it's not 100%. The answer is 87%. It's all right, 87% doesn't. Now I remind you, if you take real exams where you write stuff out and you write everything down showing me you understand the problem and you get this number wrong, you'll still get at least 90% credit. But on multiple choice, you lose. The multiple choice tests are not good. But UF won't cooperate with me to let me run this class the way I want to run it. Because you see, you remember when I offered you the opportunity to do the exams on Sundays instead of during the week? You see, if I was in fact in charge of this class, when you register for this class, you would register for Sunday exams. You wouldn't have a choice. And then you'd get the 4 hours and you'd get real exams. And none of this multiple choice garbage, but we'll let that go for till another time. Because I want you to learn, damn it. And one of the things that I need to know in order for me to help you learn is what you do and do not understand. And I can't know that from your bubbling in circles on a damn piece of paper. I'm no mad genius who can read minds. I can't do that. But when you express your thoughts on a piece of paper, I can see where you went wrong. Or instead, I can see that you went right. Hey, in my life, beside myself, you know who have been my best teachers? I'm looking at them. My students, that's who. Because until I came to UF and started dealing with large classes, more or less governed, the operation of which is governed by this dumb administration, I hope to hear this. I mean it. The administration of this university has no idea whatsoever how to serve the needs of undergraduate education. I mean it. They don't know what the hell they're doing. If I became president of this institution, the first policy I would enact is that you will lose your job if you give multiple choice exams from this day forward. I mean it. You'll give real exams and that's all. And if you don't like that, if you don't want to do the work, get the hell out of here. I don't care how many millions of dollars of grant money you got. I don't care how big a reputation you got. Out! I want teachers to serve the needs of these people. This is the future. These people who are before us. Not you and your research grant. Now, you might do some great research, but there's a good bet you won't. But look here at all these people. I mean, I say that because, well, I got to be careful about this. But in my humble estimation, over 99% of material which is published in today's scientific journals is junk. Doing novel research is easy. Doing novel, good research, that's tough. That's tough. But let's let my philosophical attitudes go past before they all come in here and lynch me. Or indeed, I would have to hope my students will fight for me and save my life. Okay? On we go. Now then. V-conc sulfuric acid solution versus V-dilute sulfuric acid solution. The question for these two conditions is, under these conditions, how does the molarity of these two sulfuric acid solution species relate? How do the molarities of these species relate? V-conc, very concentrated. Well, let's put the puzzle parts together. V-conc means the value for m sub I is a big number, small number. Big number. I want to be sure you understand this language. That means, given that this reaction is still going 100%, what kind of number am I going to get for the hydronium ion concentration? Big or small? Big. Will that hydronium ion concentration be in essence the same as m sub I for the V-conc solution? Yes. Why? Because if the solution is V-conc, the ionization extent of this reaction, which is the only reaction that makes sulfate ion in the pot, the ionization extent of this reaction is what? Very small or very large? Very small. You're damn right. So, for V conc, hydronium ion molarity is large and enormous relative to the sulfate ion molarity. So given that we asked the question like this, we can write this. Now let's go to the V dilute solution. Now how will hydronium ion molarity and sulfate ion molarities relate? Yup! Yup! Speak loudly and boldly.
Twice as much hydronium?
Twice. Right? Now the hydronium ion molarity will be twice sulfate ion molarity. Are you seeing this? The first reaction goes 100%, and now the second reaction goes 100%. So this will be twice M sub I, and this will be M sub I. Done. That's it. Now I'll write equal to or about twice because it will depend on just how dilute it is. Now at this stage of the game you should be able to calculate that molarity for which the second ionization reaction to 2 sig figs is 100%. It's not hard to do. Question. For a sulfuric acid solution, that's the only solute, sulfuric acid molecule. What is the maximum molarity for sulfate ion? What is it?
We'll have M sub I.
Nope.
M sub I.
Nope. The answer lies in examining this relationship for what kind of concentration condition, very high or very small, which sulfuric acid solution will contain the highest sulfate ion molarity, very concentrated or very dilute?
Diluted.
Don't be tricked. You'll always get the highest molarity of component species in the highest concentration solution. Right? See this? If the molarity is very high, then how will the molarity of this compare to the molarity of this? They will be, in essence, equal, because this ain't going anyplace, right? Sulfate ion equals this. All I'm asking you to do is to let this relationship talk to you for the concentration conditions which I just described. I've asked that question a number of times. Keep in mind what these numbers tell you. The higher the concentration of the solution, the higher the concentration of the solute-derived species. Has to be. You can't get something for nothing. Now then, one more question. This is taken straight from the notes. Let's stipulate that I'm dealing with a sulfuric acid solution for which the hydronium ion molarity is 4 times the sulfate ion molarity. If that be the case, what is the hydronium ion molarity? How do we determine such? Remember this? Well, if I stipulate that, can I write this? Didn't I say this is 4 times that? So I immediately know that for this solution, how does M sub I compare to the sulfate ion molarity? 3 times the sulfate ion molarity. So if this is 3 times the sulfate ion molarity, how does the hydrogen sulfate ion molarity compare to the sulfate ion molarity? What is it? 2. Twice the sulfate ion molarity. So I can go to this. Okay? Here, I got sulfate ion molarity. Here, I got twice the sulfate ion molarity. And what do I have here? 4 sulfate ion molarities, right? So I got sulfate ion molarity top, sulfate ion molarity bottom. Here I got 4 sulfate ion molarities. And here I got 1. Here I got 2, right? Watch out. 4 divided by 2. 2. How about that? So I've now found the sulfate ion molarity for this solution is 6.0 times 10 to the minus 3. And the hydronium ion molarity is 4 sulfate ion molarities. 6.0 times 4. 2.4 times 10 to the minus 2. Done. Is that all right? And you can do it just as quick and fast if you let this stuff talk to you. That means understand this stuff. If you look at this like an algebra puzzle, you lose. This is chemistry. I think you know that by now. Right? Okay? That's it for exam 1. Go get 'em.